webinars for the Irish Human Factors and Ergonomics Society for a while. We normally don't take this spot because we use it to actually invite people externally and know about each other research and progress in this area. As it happened this February, we've been invited to present about this project. There is actually, one of them is near conclusion and the other one is just a spin out of the previous. So we'll do our best because it's a topic of interest to the community, we find. So we want to share with you a little bit of the lessons learned on collaborative intelligence in the application that we've been looking at in terms of safety critical context, and both from the CISC project, but also this ROBOMATE project, which is more about the human-robotic collaboration and how to make it more let's say, intuitive and flexible and democratic in a way, easy to use. As we always say, when we present the work, it's a collaborative intelligence work also in more than one sense. The work that we are presenting is the collective results of a team of people. And these are the faces of some of the sharp-end researcher that made it possible. One of them is with me. We couldn't fit them all in the booths where we are now, but be reassured that the credit of some of the, let's say, the understanding that we present today, it goes to collectively to many of them, most of them actually, all of them, and the supervisor that did not fit in this page, but are equally important. And we can mention some of them if you want. In the different organization. The idea started in 2019 when I work occasionally also with in oil and gas in looking at control room operations and safety assessment for industrial context in the human factors field as well, and we thought that there could be a great potential for applying some of the AI capacity in those contexts, but it was also crucial to understand how. And for me, it was inspiring to read this quote from Daugherty and Wilson that I thought was actually hitting the spot in the sense of where we want to be. So it's an organization that use machine to displace worker through automation will miss the full potential of the capacity. The leaders for the future will actually those embrace collaborative intelligence and are able to transform their operation and, more importantly, their workforce. So we thought that there was a real space to explore the concept of what is this collaboration between the human and the AI, where the interface come into play in the sense of where is the machine assisting the human and where is the human needed to assist the machine for overall having a system that is maybe more robust, trustworthy, and potentially also reliable. So we thought some of the application that you'll see, there is always an interplay or a mix of both. So there is the machine assisting the human. For instance, in traditionally robotics, the intention is for the robotic to take over some of the more repetitive tasks, the one that actually induce repetitive strain injuries or musculoskeletal disorders, and for the human to assist the robotic machine in doing so. And maybe that's why we've been working in something that is teaching by demonstration, in doing it in a way that it's more intuitive from the human point of view, that doesn't require deploying a robotic engineer to reprogram the robot every time a small change in the task happen. That's where the human are better because the human are more flexible, easy to it's easy for them to intuitively perceive and react to changes in a way that should be more appropriate. On the other hand, we also thought about other spaces where decision support system, okay, the machine can assist the human, yes. You'll see now there is an avalanche of information that needs to be processed, especially in the space of alarm management. It would be useful to have AI helping to filter out, to see the woods from the trees, so to see the information that is very relevant and needs to be acted upon very urgently and the one that is less so, and to have it in a way that is transparent, explainable, that the user can really trust and consider trustworthy. On the other hand, the human needs to assist this process in a way that becomes reliable. So it cannot be based on a black box model, especially because it's a safety critical industry. It needs to be understood where it comes from and justifiable in the sense of even more traditional automation approach, input-output diagrams used for designing interfaces and alarm system in the industry as they are like rethinking about that concept. To do so, we decided to use a very action research approach, therefore, to have design of experiment to test in application, to test with participants, to test anything, any about the system was worth testing. And in fact, we ended up having several living lab, we call them. So we had the one about human-robot collaboration, took 3 shapes. So it was a telerobotic operation and the design of the HMI for favoring this telerobotic from macro to micro. And then it was the naturalistic learning for robotic arm, teaching by demonstration, and also the assessing of cognitive load in context where there is a collaboration or fully automated or a fully manual or a collaborative workspace. And then we had the Living Lab 3. So we're going to talk about one application from this context, which is the teaching by demonstration. And then we talk about another context from Living Lab 3, where there is the space of assisting the human in decision-making in control room. And we're going to talk about alarm management and the support that can be given. And also what can be studied about the HMI that are used in that context. So Ammar, the floor is yours.
Thank you, Chiara. So starting with the first application of in the human-robot collaboration. So what is teaching by demonstration? It's actually making it more flexible in terms of how the robot can learn rather than programming, how we can make it accessible for a normal user to teach directly the robot by moving its arm, and then using the demonstration as a pipeline to create a program that the robot can learn in the robotic language. So if you see this diagram, so the human user, any normal user can demonstrate what action is needed to be performed by the robot, and then it automatically segments and creates a program that is taught to the robot, and the robot executes it more flexibly. So even if the position of the things or objects changes, it can flexibly adapt to the changes and then perform the same execution as has been demonstrated by the human user. The right, you can just see a hypothetical, like what's the framework, how it does it work. So when you demonstrate in the learning phase, it segments out different profiles and tries to learn those basic movements as a normal human user would learn, like from moving from one point to another point with a certain trajectory, how to learn that trajectory and that behavior, and then how to combine those different trajectories together to perform a, a larger task. Just to give a demonstration by a video. So the framework that I already mentioned here before. So the offline learning works as the human user would demonstrate the robot to perform tasks such as picking and placing, insertion, or erasing, etc. And then during the execution phase, you can see a normal execution where the robot would perform exactly what has been demonstrated by the user. And then there is another part that is called reactive execution, in which while the robot is performing the task, the user can change the environment, and there can be different changes in the environment, and the robot adapts to those changes. So it's more like how to flexibly make the robot learn the environmental changes and learn from the demonstration to do the task more flexibly. And then later on, once you have demonstrated key skills such as picking an object or placing an object, you can create them as a modular task that can be combined later on to perform more complex tasks, such as kitting, that is picking and placing different objects and creating it as a one form, or maybe drawer pick and place. So opening a drawer was demonstrated once by a user, and then picking and placing was demonstrated in another set, and then we can combine those different tasks together to perform more complex trajectories. So that was the part from what we did at the robot's perspective, like how to teach the robot well, but to give a good demonstration was another factor that we needed to for the user to learn. So if we want to implement this system in an industrial environment, how can we make the users that doesn't know much about how to train this robotic system more capable of learning how to give a good demonstration? So what we do here is create an HMI for the users. So the blue curve you see here, we'll just play also the video at the bottom. So the blue curve that you should see here is the demonstration given by an expert, and then the red trajectory is the one that is given by a normal user. That may be a newbie for the demonstration, or maybe an expert, but they would learn how to give a good demonstration through this HMI. So once they perform this task, that is stacking a cube on a different cube, it's a digital twin of the real robotic cell. So the user, once they move in real time, they can see the objects moving. They can see the how did they perform this trajectory, and then after they have performed this demonstration, they can click on provide feedback, and they can know every bits and pieces of how well did they perform the demonstration. And once they can see how good was their moving, how good was their velocity peaks or execution time as compared to the expert trajectory, they can improve in the next iteration. So this is where we try to improve upon also the HMI, how to give better demonstration to the user so they can learn to give more and more better trajectory as closer to an expert. So what we are trying to assess here are like different modalities. In terms of robot learning, it's task accuracy, like how good or bad is the task performed by the robot, and the task completion time, how fast they can perform that task, and the logs of the errors, such as if there is a missed grabs or object collisions, etc. From the human point of view, we are trying to assess the mental workload through surveys such as NASA TLX or some similar tools, and then time is spent during the teaching, how complex or how longer would it take for a human to give a good demonstration, and then error feedback during teaching, such as if we can have a live feedback or ergonomic assessment of how to give a good demonstration, etc. I think that's all from my part. Now moving on towards the next application of the use of a digital twin for testing different collaborative intelligence configurations in the process control environment.
Actually, Ammar was involved in this also. So what we did there was, first of all, starting from the status quo. So what is the situation in industry? It's a situation that I know because thankfully I've been involved still in some applied work with them. The idea is, as human factors expert, I think we did fail a category of industry worker badly, and is the control room operators, because we set very good guidelines of saying, okay, let's say it's to be expected that an operator should not deal for more than in 10 minutes, there is a maximum number of alarms that should be acceptable for an operator to deal with, okay? And this number of alarms, I can assure you, is nowhere near the actual value that we observe. So as you could see, these are all 10 minutes window intervals, and we're always constantly in ratio that range outrageously high. And you can argue, okay, this is a control room, there is more than one operator, potentially two. Still, it's tremendously higher than the guidelines that have been set and revised even recently by colleagues. So, and even when you look at the count of alarms by severity, and you say, okay, a lot of this is noise, which is low-level alarms that could be cleared out, etc. No, we actually found the majority of those alarms are actually in the category that is considered to be critical, the red one. So there is a problem. There is a problem how alarm rationalization is run, how at design stage we decide what gets alarmed, what doesn't. And although there are human factors guidelines for this, we still don't provide enough of, let's say, framework for helping the design and also supporting the operator when they have to face the amount of alarms that they get. So we looked at looking at other methods, like for instance, okay, the filtering, the clustering, the prediction of trips, so even deciding priority on the basis of how likely it is that this alarm will result in a trip, and how long do we have from the appearance of the alarm till the appearance of a trip. And yes, even things like correlation matrix is able to filter out immediately alarms that appear to be even 100% correlated with each other, which means, okay, they should be clustered or organized differently. So this is a low-hanging fruit that I think we need to explore and apply even now, okay? But there was also another aspect to this, which was the prediction, the part of the prediction model and how they could be used to enhance decision support in responding to alarms. Even, for instance, in the sense of the detection of causes or suggestion of possible course of action, etc. So originally we set out to set a living lab on this also. So we had an actual simulator of a plant. Obviously, we're not actually doing anything unsafe on real plants. And we set 3 scenarios on different situations. This is a formaldehyde production plant. We focus first on the ethylene section of the plant, and then on the reactor. So we had 3 scenarios. The first 2 were on the same system, and the third on a different system. And we had a control group, group 1, that had no alarm rationalization support, no electronic procedure support, just paper procedure, and no decision support system. Then we had a second group that had alarm rationalization and paper procedure, just to even see the effects that it has on improving their performance. Then we had the third group with alarm rationalization and electronic procedure, and also the paper. And then the fourth group was the one with the decision support system. Decision support system that Ammar was directly involved in supporting and programming for a section, and we'll discuss it later. But before we step into that, it is important that we discuss with you, human factors expert, what you think is a human in the loop. What is the human in the loop concept that we have in our head when we think of those systems? Because I must confess that even for ourselves, among ourselves, this wasn't 100% clear. Okay, we worked on certain hypotheses, and those hypotheses turned out to be maybe, revisable. So, for instance, in this definition, I'll try to read it. Human in the loop decision making is where content is flagged by the AI, and the human moderator review what has been flagged and confirm whether the machine was correct in order to enhance the algorithm decision making. This is one of the most widely used concepts in industry, in the way we are developing such an AI algorithm. But I must challenge you, especially because you are in the human factor society, if this is how you envisage the concept to be, okay? Really think about it, and please write for us in the chat what you think it is. Because, and I will keep you waiting, but we come across also a different possibility. So human in the loop in automation allows, so this is a different definition that, again, I found inspiring, okay? So the true human in the loop automation allows human intervention to execute actions and control the entire workflow by allowing ad hoc application of human judgment. And by doing this, it can be more flexible and powerful. There is a difference between those 2 definition, and it's might not be clear, but it became clear to us when we saw it in action, okay? And we like to see where is appropriate to apply there could be some places where it's appropriate to apply the first, but we must acknowledge that that's a limited concept for human in the loop, where the judgment of the person required is so limited that sometimes you're better off automating, especially because when it comes to applying responsibility for decision making, the decision making has to be there and has to be a true real judgment process supported. And so we saw this, as I said, in the way we try and configure group 4, the decision support system, for our own simulator. So there was a lot of good work that went into this, and there was Joseph and Anders and others and Gabriele, they were actually involved in developing a model, underpinning model of the functioning of the part of the tank that we had to, through the influence diagram in Bayesian network, so explainable. And then Ammar actually worked with the data generated by the simulator to verify, okay, if there is a situation of, for instance, the lack of pressure within the tank, which is a dangerous occurrence because you can leak ethylene. How do we prevent this from happening? What do we suggest the operator to do? Even in the sense of giving a precise value, saying, if you have to reestablish the flow, what should that flow be? What does it look like, the flow? And that's what we did. So it was in the, so you can see this is in this page, the configuration of the experimental setup, the overview screen in the center, the mimic specific for each subsystem on the left-hand side, and on the right-hand side is the trend and alarm page. And in the alarm page, we had the decision support system that in some cases even anticipated the alarm. And in that sense, we wanted to show or to study, and this is the part that if you want to ask, Ammar can explain in more detail on how the actual recommendation went to the detail of providing even the value that the operator just simply had to execute. And what we wanted to observe, and we actually set up the design of experiment to try and observe it, not only is how good or bad the performance was, but also the situational awareness. So at specific point in time, so few seconds after the alarms appear and another point after we see the operator responding to certain things, we ask, we have a process for the situational assessment, performance assessment, so that we used. And what we wanted to see is comparing, okay, the performance in itself and the situational awareness for the operator responding to those alarms. And for us, the finding was kind of, we weren't fully expecting this, okay? So we noticed, yes, for scenario 1 and 2, the response time of the group with the decision support system was way faster than the others, which is great. Consider the scenario 3 is fundamentally conceptually different because it's a survival scenario. So it's a scenario where the operator is asked to maintain a stable condition in the reactor while a field operator fixes the situation. So the situation is survival, which means the people that last the longer succeed. And actually, and the scenario is more complex because it has a higher rate of alarms. In this context, group 2 did way better than, okay, group 1, which is the control group. It's the group that has been given no support in a sense, but also group 4, which was the group that was given the decision support system. And we have a few hypothesis explanation to share with you, but for us in itself, this was a very, very thrilling or interesting finding. And the same in the sense of the consequences for the first 2 scenario, which are compatibly low complexity. Group 4 outperformed all the other groups. When the situation became more complex, group 4 did not have the same level of good performance, and more consistent performance came from group 2. So the one with the alarm rationalization and the procedure paper. And when we looked at the situational awareness, we saw something, confirming this fact, which is to say that often in group 4, we did not find the best situational awareness. Best situational awareness was somewhat in group 2 and potentially group 3, while group 1 and group 4 had the lowest. So we also did some physiological analysis of, for instance, eye tracking. We saw different strategies. So for instance, these are 2 different participants in the same group with the decision support system. You can see the one on the right-hand side tend to look at the suggestion and execute the suggestion, while you have another one on the left-hand side of the screen here that actually has potentially trying to forage information and make his own mind. And this might work in his favor or might not, because sometimes by the time he gets to execute the suggestion that was presented, it might be too late, or the situation might have changed a bit. So so important, this for us was very important, lower situational awareness. The task load is less, obviously, when you have the decision support system, and you tend to solve the problem earlier, but in complex scenario, this not necessarily always all true. I'll save you because of the time, the other findings, but let's just say there was interesting findings also in the analysis of digital procedures versus paper procedures. So unless the digital procedure are really well aligned, guess what? We get more information from sometimes the paper procedure because the screen, the space for the procedure is small and it's limited to one procedure at the time. While on a piece of paper, sometimes the way the operator tended to use it was to have more than one procedure open up and they could look at concurrently, and that probably was better. So in general, we also found that there is a space for us to improve our work on function allocation and the criteria to give function to human or automation or flexibility interplays between the two. And how we can improve transparency of this decision support system, how the decision support system might be changed towards something that filter out information and provide a clarity on the strategy, the target, and maybe then doesn't give, we call the monkey instruction, but doesn't need to give the specific value, but probably refer to the knowledge that we need to rely on, that the operator still needs to have. And also we have to remember the fact that in this interplay between intelligent agent, intelligent autonomous agent, and operator, if we want the operator to retain skill and autonomy, they need to be asked to do stuff, even when potentially might not be necessary. The same way we ask pilots to land an airplane when we know that the automatic pilot might be perfectly able to do so, because of the problem that us as human use it or lose it. So this is true. So we need to even find the right balance of what we ask an operator, what is reasonable, what is the task that is worth retaining and necessary to retain in terms even of competency. So that closes for us, and thank you for your patience and your attention, and we really would like to open the floor to some interesting questions or discussion.